thanks very much for inviting me and for coming to the talk. So I guess we're switching gears and coming back a little bit to the more kind of mundane problems of the Earth, and in particular long-range coarse-grained forecast for the climate. So before I begin, I would like to thank a few people for the contributions to the project that I will present. This is joint work with Andrew Maida at Courant, and I would also like to thank my colleague Boris Kerskoring and Professor Ilya Khorenko at the University of Lugano in Switzerland for various discussions about predictability, and Raphael Abramov at the University of Illinois in Chicago for providing us with a data set that I will be talking about later. And also my co-advisor for my PhD, Paul Fisher, who allowed me to still use the computational resources of the Argo National Lab to do the calculations for this project. So this is the outline of the talk. I will start by saying a few words about various types of problems we have in predictability in the climate, and in particular I will distinguish between the so-called initial value and forced boundary problems. So we heard a number of those during the last 2 days, and they were mostly focused on this side of the spectrum, meaning like the more kind of long range where external factors are actually important. And I will then give a description of predictability as additional information beyond equilibrium statistics. Then I will spend some time talking about how we can use information theory to quantify what we mean by predictability in this context. And I will try to draw a few analogs between the problems that, the traditional information theoretic problems like the communication across a channel and compression of signals, and I will try to make a parallel between those and climate models and biases in climate models. And then I will say an application for studying the regime behavior in a simple simulation of an ocean basin, where we try to look at making decadal range forecasts about the large-scale circulation, and also we study the error in Markov models for this system. So, I mean, the general techniques I will present here hopefully are of interest to other areas besides climate science. Whenever one deals with dynamical systems or clustering or information, and also when people are interested in assessing the fidelity of approximate models. So this is a useful way of thinking about the various types of problems one might encounter in climate forecasts, is to make this table where on the horizontal axis, so to speak, we have the lead time. So this is how far in the future we're interested in making predictions, and lists the various type of things we can do. So on the one hand here, all the way on the short range, we have the usual weather forecast. So this is pretty much an initial value problem. So if we want to, given the state of the atmosphere today, we want to predict how the weather is going to be tomorrow or the day after tomorrow. So here, the details in the initial condition are very important. However, because the climate is a chaotic dynamical system, even arbitrarily small uncertainties in the initial conditions will pretty much dwarf everything after about 2 weeks. So if we want to go to the extreme, when we want to make projections for several decades in the future about the climate, there's not at all any importance about what the weather was in, let's say, in Manhattan today. At this side of the problem, what is more important is what is the external factors, what are the boundary conditions. For example, what will happen as a result of us pumping CO2 in the atmosphere, what will that influence over the next 60 or 70 years. So I'm not going to talk to neither of these problems. What I'm going to be talking about is this kind of regime in between, which is somewhere in the region between, let's say, 5 to 10 years, where you don't care so much about the details in the initial state, but there is though some residual memory. So you care only about the short, coarse-grained aspects of the initial conditions, and also you're not looking so far in the future where the things like climate change will impact you. So there are a number of interesting phenomena that lie in this category, which may have very real consequences when it comes to our day-to-day life, because they influence the climate on scales like, let's say, the Western US, or big, several thousands of kilometers. So, and for this type of problems, what is more important, rather than the effects of the external factors, is the internal variability which comes because of the nonlinear nature of the climate dynamics. So, an example of this type of problem that was mentioned already before in the morning is the Pacific decadal oscillation, which is a so to speak a long-lived El Nino pattern, which might it's still under debate exactly what is causing it. It's not it's an active research problem, but it can influence the climate over periods of lasting decades. And so it's important to understand processes like that, especially if we want to distinguish between the anthropogenic influence on the climate versus something that is purely due to the internal dynamics. So this is just an example of the type of questions one might be interested in asking. Now, to abstract this a little bit more, what we assume is that the climate is governed by some very high dimensional nonlinear dynamical system, which we can not observe, of course, in every detail, nor do we want to. But on the other hand, what we do, we make some set of partial, incomplete measurements. So our knowledge of the system is never exact, even at the initial conditions have a large amount of uncertainty in them. So based on these incomplete observations that we make, let's say some kind of temperature data or wind data, we want to predict certain large-scale, coarse-grained observables in the future. And in this particular talk, I will assume that these are scalar observables, like let's say the average temperature over an ocean basin or something like that. But this is not necessary. So in climate science, and especially for the problems that I will be talking about, where the forced response is not important, our null hypothesis, so to speak, is not a uniform distribution. We assume that we can, go outside and sit down and get any observable that we want to measure. We can compute its equilibrium distribution. So we have some knowledge. Now, when we make a measurement, the knowledge that we have about that variable changes, so to speak, discontinuously. So if we go and make this measurement S, instead of having this equilibrium distribution, we have some other conditional distribution, which in general will be more, let's say, more informative than just the equilibrium. And in particular, our measurement will tell us something about the value observable at some time t in the future. Now, as the time grows, that distribution will relax eventually towards equilibrium. So there will be some information loss as time goes on. So fundamentally, in order to quantify predictability in this context, we need some notion between distances between distributions, or a way of measuring how much information, let's say, this red distribution has compared to the blue. So information theory is a natural setting to do that. So I will spend a little time explaining that. So I guess in this audience, this is a well-known material for almost everyone, but information theory was pioneered in the late 40s by Shannon as a theory of communication, effectively, where this notion of, which is well known by now, of entropy was introduced to characterize the level of uncertainty we have about a physical system. So today, what I will be mostly using in this framework is a related concept called relative entropy, which is a measure between, let's say, a quote-unquote distance between two distributions, which has some very useful properties when it comes to quantifying either predictability or errors in models. Now, one of these properties is that relative entropy is an invariant under changes of the observable that you want to predict, assuming, of course, that the transformations that you're making are invertible. So this is nice because when we're talking about, we don't want ranked models, or we don't want our results to depend essentially on A, what we choose. As long as we compare equivalent observables, we want to get the same answer. So this is one attractive feature. But what is more interesting about this quantity is that it has two very useful interpretations. I guess these were already, at least one of them, mentioned today. So the first interpretation is when we do Bayesian updates. So if as a result of an experiment, I go out and make an experiment and I observe some data S, and I have a posterior distribution, then the relative entropy between my posterior relative to the prior distribution gives the amount of additional information that was achieved by the measurement I made. So this is a natural way, so to speak, of quantifying how much knowledge that particular measurement will give for the observable in the future. Now, there is another interpretation of relative entropy, which says that if I have a model, which is a biased model, and it produces some distribution for my observable, which is different from the one from nature, then the relative entropy of the distribution from nature relative to the model is a measure of the lack of information or error in the model. And what is important to mention here is that this dual interpretation is somehow related to the fact that entropy as a distance metric, again, it's not really a distance, it's not symmetric under changes of the in its argument. So it's different depending on how you make those comparisons between the distributions. You get a different interpretation. So now this was again talked to earlier. This concept of mutual information. So of course, if measurements can take different values, and different measurements will provide us different amount of information about an observable. Now, if we take the expectation value over all possible things that we can measure, then we get a quantity which is called mutual information, and essentially is the joint entropy between our prediction observables and all possible initial data that we have. And this is an objective measure of predictability of this observable given the measurements that we have at our disposal. This has a nice, an intuitively nice property that the mutual information vanishes if and only if the initial data and the observable are statistically independent, which is fits with an intuition that if we make a measurement which is statistically independent from the thing we're trying to predict, then we shouldn't get any additional information. And this is a hard object to compute because of all the multi-dimensional integration that, two rounds of integration that have to take place here. So I will discuss later how data clustering can help us when we want to make long-range coarse-grained forecasts, how data clustering can help us beat this curse of dimensionality, so to speak. So here's the, let's say this is the one or two slides that I wanted to take away from this talk and then maybe go to sleep. Which I find particularly interesting is this analogy between coding theory and predictability in dynamical systems. So, which is not, it has been known, I guess, for some time, but now it's getting used to applications like the climate and so on. So, the relation, the analogy are, between complexity and uncertainty in a variable, which comes about from entropy. And the other analogy is between the bandwidth of communication, the maximum rate of information that one can transmit across a channel, which is measured by mutual information, and predictability. So you can think of, so to speak, the prediction problems as a kind of like communication channel where on the one hand you have your initial data and on the other end of the channel you have the prediction observable, what you want to predict, and the predictability is fundamentally related to how much information can go down that channel. Now, this is all in the kind of a perfect model environment. Now, what about if we have these biased models? Here, the analogy is between coding using a suboptimal code and using a biased model. So it is a well-known, again, result from coding theory that if you don't use the right code to encode a message, you will have a penalty in so to say, the bits that you need to encode the message. Here, we can analogously measure the error in a model by a similar metric. Okay, so just to repeat, the basic measure that we'll use here to quantify the skill of predictions is the relative entropy between the conditional distributions on our measurement and the equilibrium distribution. So this will be a time-dependent quantity. So the further you go in the future, you expect this measure here to eventually decay to zero. And this has been, this type of metric has been, I guess, since the early 2000, being used in a climate application. So what is nice about this property is that, which in some sense, you can think of it as even being more fundamental than the ordinary entropy, is that relative entropy satisfies, you can prove that under certain conditions satisfies a second law of thermodynamics in the sense that in a dynamical system, it is non-increasing function of time, provided that you have certain conditions about the Markovianity of the system, meaning that you have to be able to say that given my state at the present time, I can fully, there's a unique way to evolve the system in the future. And this will not always be the case in the applications that I will be talking about, because we don't have complete observation. So this observable here is not a complete autonomous dynamical system. It will be some function of the state of a dynamical system. So it can have memory effects and other non-Markovian features, but the general behavior is that we will have a decaying and predictive skill as a function of time. So here's now the part about making a long-range coarse-grained forecast, which basically is what we will use to beat this curse of dimensionality of the initial conditions. Now, if you want to make a short-range forecast, like the weather about tomorrow, details are really crucial. I mean, our ability to make better and more reliable forecasts in the weather has a lot to do with the fact that we have much better measurements about what the weather, the state of the atmosphere is at the given time, so we can use that, fit it in our models, and advance it for the future. However, that memory is lost after about 2 weeks or so, based on the chaotic dynamics. The details don't matter. So for long-range forecasts, we can just forget about the details and just think about all the possible set of initial data in a coarse-grained manner. So the idea is that instead of focusing on these details so much, use some clustering algorithm to partition our phase space into a small number of clusters, and then consider probabilities that are conditioned only on which part of this coarse-grained partition you are on. So this makes automatically this problem of evaluating expectations values with respect to the initial data a much simpler problem, because now we just have to integrate over a set of discrete probability. So, and this is a generic strategy. It doesn't matter. I'm not going to. It will not be dependent on what strategy you use to make your clustering. We heard this morning already approach which is tailored for, let's say, data on a sphere or so on. But given that you have produced a partition, it is a way to measure how much skill that partition has for making forecasts. So in this particular example that I will be talking about, I will use a variant of k-means clustering. So for this problem of the ocean data, it turned out that it was a good working algorithm, but there are several other approaches one can use. But it's not going to be just standard k-means clustering. We're going to do what we will do is collect data initially over some time, this delta tau, and average them out. This is in order to beat, so to speak, the very short frequency fluctuations. And we will use all these information theoretic metrics to optimize to find the optimal window of data that we have to collect for the given, to make a prediction in the future. And that will depend both on the observable that we want to predict, and also it will depend on how far in the future we want to predict. So, I mean, intuitively, if you want to make a relatively small range forecast, you might want to collect data over a reasonably large time, because persistence, a lot of these systems are persistent, so it might give you more information to collect data over a longer interval. Now, a similar thing can be employed also to create, to find the centroids in this partition of data. You can build a one-parameter family of partitions by choosing a running average window, and take some training data and vary that average window. So you will get a different partition in each case, which then a posteriori, using this relative entropy, you can decide which one has the most information for the prediction that you're trying to make. And once this exercise is done, for each of these cluster conditional distributions, you can compute the expectation value, and you take basically the skill in the partition as the mutual information between your initial affiliation to the cluster and the value of the observable. So, and intuitively, in the far, as time goes to infinity, infinitely far in the future, you expect that you won't have any residual skew, or equivalently, that your cluster affiliation and the value of the observable will be statistically independent, which will happen because of the chaotic mixing and in the dynamics. So. Here I will say this is some reasonably simple application that we tested this framework on. So here's this contour plot is the wind time average wind stress over the world's oceans, and what you can see is that a reasonably prevalent pattern is that you have in the Atlantic or in the Pacific this westerly winds. So the solid contours are westerly winds coming in the mid-latitude, and then this easterly winds in the subtropics, and this create a forcing in the ocean basins, which ends up creating circulation patterns and jets like the Gulf Stream in the Atlantic or the Current in Japan. And people are interested in even in this kind of like time-independent setting. So here we don't discuss, we assume that the forcing of the wind on the ocean is caused. So people are interested to find the long-range dynamics in this problem because, for example, part of what we are seeing today, part of the fluctuation that we see in the climate may be due to this type of behavior in long-range, low frequency internal variability. Of course, most likely it's not just that, but it's important to at least understand how much of what we're seeing is due to the internal variability. So in the toy example that I will talk about, we will take some basin, let's say the Pacific here, and we'll model it as a box where we're going to force that box with a wind forcing that is more or less mimics what is the average wind over the Pacific, and the simulation will develop a jet which will be analogous to, let's say, in this case, the Current in Japan. So to say a couple of more words about the model that we use, this is the so-called 1.5 layer model, which is probably among the, it's a standard, very basic model for the ocean. Basically, it models, the reason that it's called 1.5 layer model is that it models the ocean as two different fluids, but the lower fluid is supposed to be infinitely deep and at rest, so it's kind of like sitting there, whereas the top layer can move in the horizon in a 2 dimensions. Yeah. So here we're looking at from the top. This is the domain of the simulation, and it's showing in color the stream function. So the stream function is basically along constant lines of stream function. The velocity vector is tangential. So you can think of this is a jet that develops in the model. You can think of this point here, let's say, as being Cape Hatteras, where the Gulf Stream emerges in the North Atlantic. And the goal will be basically to study what is the intrinsic predictability in this problem. So I have a little movie that I can, I guess. Okay, so this is a little movie that is showing a realization of this model. So you can see that you have this jet that is coming out here and it's interacting with various eddies that are in the domain. And if you look at how the time goes here, it's pretty long. Okay, I'll try it. So the idea is that this, the configuration of this system will be undergoing some kind of metastable behavior between different regimes where this jet is either strong and elongated or weak and meandering. And this might be actually a feature of the real ocean. Of course, this is extremely simplified in this model, but you can imagine that a lot, let's say if this was the Eastern US and this is Western Europe, a lot of what happens in Western Europe might actually, over a period of a few years, might actually depend to some extent on the configuration of this jet. So, yeah. Oh, sorry. Okay. So, and in fact, in this particular model, this people have been studying for quite a while now, mainly empirically, and they have found that there are three basic type of regimes or metastable states of this jet. One in which the jet is very convoluted and meandering. One which is more kind of like it looks like the time average flow and it has moderate values of the energy. And some other state which is extensional and it goes deep into the basin and it's characterized by high energy. So here there's a histogram of the distribution of the energy, the kinetic and potential energy in this model. What's characteristic about this type of problem is that you have the statistics are pretty much unimodal. So the distribution is unimodal, and yet you have these distinct kind of regimes. This is because the dynamics here are fundamentally non-Hamiltonian. So it's not necessarily the case that you have extrema in the PDFs to have distinct regimes. And in these three columns are corresponding snapshots from this distribution. And even though you wouldn't have guessed, but they look just from the distribution, they look very different in terms of the spatial configuration. So for this data set, we run the model. This is a true, so to speak, nature in this application. But we want to do the clustering and using incomplete observation. So our incomplete observation in this case is projection of the state of the system into the so-called empirical orthogonal functions, which are capturing maximally the variance. So we take the first 20 of these so-called EOFs, and we call that our observation vector. So we assume that we don't have knowledge to the full fine-grained dynamics. We can just observe the leading EOFs, which represent the more large-scale features of the flow in this problem. So yeah, this is just summarizing that. And we want to, given these observations of these EOFs, we want to partition them in a way so that to make predictions about these other observables, like the energy or taking the marginal, one of these principal components. So yeah, we have a 20-dimensional set of initial data, and we do scale our predictions. So this is just a sketch of how these partitions look like. So this is the cloud of data in equilibrium. So the equilibrium distribution of now, in this case, of the first PC, this is unimodal. And we will partition it using the simple algorithm that I just described earlier, which has this one free parameter, the window that you can smooth the data when you do the clustering. And it turns out that this is actually crucial to make informative partitions. So we can vary that window that we smooth the data, and for each value compute the relative entropy and choose the partition that buys us the most information about this problem. So here I'm showing an example where I'm plotting some, in color-coded, some of the different sets from a partition that had 7 classes, and you can see that if I look at these are the conditional distributions on the partition, they, even though the equilibrium distribution was unimodal, you get this characteristic type of conditional PDFs, which are hopefully buying you some information about this system. And as I said, using this approach, what one can do is, for the given observable that they want to predict, find the optimal. If you had different partitions to choose from, you can find the optimal one. So here, the parameter that we can vary is how much we allow, how much initial data we collect and we average out. So this is this delta tau here. And typically what you find is that there will be some non-monotonic behavior where there will be a value of averaging that will provide the most information about the observable in question. And that will change from observable to observable. So there won't be one partition that will do the job for every observable. Also, what is useful about this approach is that it can provide some intuition about how many clusters you want to put in this problem. I mean, typically, what one finds is that as you increase the number of clusters, of course, you get more and more information, but there is a point where the additional information that you get is really minor. So it provides you at least some guidance on where to call it a day and say that this, for a coarse-grained description of the system, it doesn't make any sense to increase the number of clusters further. But it does that in a as far as objective way as you could hope for, at least. So, and this is now the result for one of these partitions that I showed. If I take the stream function and compute this conditional mean on this partition, we find that the regimes separate naturally into things that people would associate with a meandering phase where the jet is really I don't know if it's even visible in the projector. It's doing a kind of like meandering path and has a lot of variance. This is the standard deviation of this flow. Then you have on the other extreme one other regime which is very deeply extensional with little variance, and one other regime that is somewhere in between. So the results that you get out of this procedure agree, at least in this problem, with what people had determined earlier using a more empirical type of approach. And now, what about the predictive skill? So in this diagram, I'm going to look at, say, energy, which is one variable that people might be of interest in this problem. In this diagram, what we show is the entropy in the z-axis. So this is high skill as a function of forecast lead time. So this is how much in the future you want to make a prediction, but also as a function of how much initial data, what is the initial window that you use to collect initial data. And what I'm trying to show here is that this behavior of the predictive skill is not monotonic, and it also depends a lot, well, not a lot, but at least there is some dependence on how much data you collect initially. So for short times, this orange curve here shows the maximum with respect to this running average window. So for short times, you get the most informative prediction by collecting data over, like, let's say here is about 1,000 days or 3 years. But as time goes on, it doesn't really make any difference whether you base your predictions on immediate kind of like data or you collect a lot. And I think intuitively this can be explained because if you collect data for a long time and you average them, you are favoring persistence in your predictions. And because of the nature of this problem that has low frequency dynamic, if you want to make short range predictions, persistence is probably a good thing, and this information theoretic quantity reflects that here. One other thing I should mention is that this if you look at just one section of this diagram, you will see that it is non-monotonic. So this means that this variable in particular, energy, is non-Markovian, which is kind of expected because we're taking a full high-dimensional state space and we're integrating it into a single quantity. So we cannot expect that this is a Markovian quantity that would. Yes.
You measure time in days?
Sorry?
Do you measure the time in days?
In days, yes.
Yes. Have you tried to change the unit, to see how it changes with the scale?
Well,
so for
this
example,
is
instead of, because if there is a process that is interested, the evolution is interesting over years.
Yes, so for this problem, this is the natural, years is the natural scale to use. So this is like 3,000 days, this is a decade. So this is, for this particular problem, this is the natural day, time scale that people, so in the ocean, the predictability in this type of situation is like up to a decade. If you want to go beyond a decade, then you have to think about more about stuff like CO2 and external, maybe anthropogenic factors and so on. But if you want to do like predictions over maybe 2-3 years or that kind of ballpark, you can pretty much it's a reasonable assumption to treat it as a system that is purely driven by internal dynamics. So here I'm showing that this skill as a function of time that it decays, but it decays so at a rate which is significantly slower than what you would expect just from the autocorrelation function. So there is predictability in this problem that extends beyond what one would expect simply by plotting autocorrelation functions. So okay, so I'll just mention this briefly. So what people do, say you have this data, you have this simulation, you want to get some description of the dynamics that's a little bit more intuitive than just looking at the simulation. It's a common approach is to make Markov models for the transitions between those regimes. And I guess what I want to just briefly mention here is that you can use the same scheme to test the validity of these approximations and compare different kinds of Markov models or any other approximate models. Could be some autoregressive model, whatever reduced model you want to use. And this is done by this, again, with this relative entropy, but now it's with the dual interpretation, which measures information loss or model error, which is more related to the kind of like, in the coding theory analog is the suboptimal coding of a message, so to speak. And here I just have two examples. One where you produce, let's say, two alternative Markov models, and if you were to measure the predictive skill, just assuming that the Markov models were reflecting the truth, you would say that okay, this model here with 7 partitions is better than this model with 3 partitions because it has more information and also decays more slowly. On the other hand, though, if you look at the error that this model gives you relative to the true dynamics, you will find that the red model is always erroneous, and in fact is systematically biased as you go far in the future, which is a really bad thing when you want to do long-range forecasts. You better be able to capture at least the equilibrium correctly, because if you use a metric of skill relative to equilibrium, if you have the equilibrium wrong, then your metric is going to be wrong for whole time. On the other hand, this other model may be not doing so discriminative predictions, but at least for short times or moderately short times, the dynamical error it produces is smaller than this other model. So one can use this approach to test various strategies for building reduced models. So this is pretty much what I wanted to talk about. I wanted to motivate the use of information theory to quantify predictive skill, and in particular making analogies between dynamical systems and channels and coding. And also to illustrate that with, if you want to make long-range coarse-grained forecasts, if you can beat, so to speak, the curse of dimensionality by using data clustering. So you instead of looking at detailed initial conditions, you only look at the system at a coarse-grained level and use that for your initial data. And there was in this application of a simple ocean model, we found basically circulation regimes using this procedure that agree with what people had determined previously empirically. And I also said a couple of words about how one can assess approximate models that one would use to try to understand these low frequency dynamics. Now, this was all in the context of a relatively simple model. Now we have some work which is ongoing to extend these approaches to more comprehensive general circulation models where, among other things, you will have time-dependent statistics and higher dimensional spaces and so on and so forth, but this is a work in progress. So with that I will close. I have some references with a number of interesting articles about predictability in the climate, and these two papers are basically the material that I presented here. So thank you.
Some more questions for? So how far, you said you could have got to 1,000 days predictions that are reasonably well with this model, but how far out can you go?
I think, well, at least with this, it depends on which observable that you are interested in predicting, but I think in this model you can go up to 5 years or 7 years for the energy, which is one observable that people are interested in. But that one can come tomorrow and say I have a better partitioning algorithm that maybe they can do a better job, and this framework will allow you to at least compare these algorithms in a objective way, so to speak, and measure how much more information this clustering algorithm can produce.
For the video, I think you set it up so that you have 3 clusters, 3 regimes.
For the video?
I mean, for the model, the circulation currents.
Right. I mean, this came out as a product of the analysis. We didn't put it a priori.
Yeah. But you did reference the first principle component.
So, you mean, sorry, in this part here?
Yeah.
So I guess this one I just used as an illustration. So I mean, we took the first 20 principal components as a incomplete observation of the system, so we don't have access to the whole state, and we use those, this 20-dimensional vector. These 20-dimensional spaces are space of initial data. So we partition that space into different, let's say, in this case, what I'm showing is a 7-state partition. I'm not plotting all of the states because it's would be hard to visualize. But once you make that partition, you can look then at the properties of the circulation in each of the elements of the partition, and it agrees with what people were finding empirically before.
I was just wondering whether you were doing eigenvectors, but it sounds like you've done 20.
Yeah. Yeah.
And you take 20 to try and quote unquote penalize yourself, or
Sorry.
why did you choose to take 20?
I mean, we tried several cases between 4 and 20, and I mean the reason I think stopped at 20 was because the first time I started working with this project, I was given 20. So I don't think there's I think you could do a good job with fewer than those. The results don't really change once you know, at least for this long-range forecast, which is probably, I guess, because the memory of this, it doesn't matter, you know, for your predictability, you don't get a lot of long-range information from the high-order principal component.
Well, if you look at your eigenvectors, you just see when how much variance you're explaining with each piece, you kind of see what variance you're cutting off.
Yeah, so here I think we're cutting, I mean, this is an important point. I mean, here I think we're capturing about, I would say, 90% of the variance, but what is, in several of these applications, you can have, I mean, variance is not correlated necessarily with predictability. So you can have components that have a lot of variance, but they're not at all they have very little predictability. And in this particular problem, it happens that, in fact, the components that have variance are also the predictable ones. Like this PC1, for example, is the most predictable, and it carries also the most variance. But in more comprehensive models of the ocean, you can have, it's been documented that the leading principal components, in fact, are not the ones that are interesting from the point of view of predictability.
This is a well-formulated question. I'm thinking of that, but I'm just wondering if there are quantities that could be derived from the calculated quantities that might include prediction. Does this formula somehow automatically take that into account? Like, for example, maybe the shear says something that would help you to predict. And can you compute it from the output of your codes? Is that somehow automatically taken into account?
I mean, so what this thing does is more like, if you want, a posteriori assessment, in the sense that it won't tell you which are the variables that you can predict, but it will tell you, once you've chosen certain variables, how much information you've got, as opposed to, say, choosing some other set of variables. And you can, you know, try, say, if I have like 20 pieces, how much information do I get if I go to 25 pieces? But I agree, this is if you are in a real, like, complicated problem, finding, you know, which observables you want to put in this is going to be a highly non-trivial exercise.
It's just that in some sense, when you have the wind field, you also do have the shear field. So
yeah. So
I'm just wondering, is there some way to formulate?
So, for example, yeah, I mean, if some of the information is redundant, presumably, I mean, I haven't tried it, but presumably by including redundant variables, you would see very, you make these plots where on the one axis you plot information, you would see little change, little additional information if your variables happen to be redundant. I would